Welcome to the deep dive. You know, when we look at legacy mechanical systems, like an internal combustion engine or a steam turbine, or even just a bicycle, the diagnostics are inherently tactile.
Right, yeah, you can physically see the problem.
Exactly. You throw a rod, you see the hole in the engine block. The gear strips, you find metal shavings in the oil pan. The failure modes are, macroscopic.
You're right there in front of you.
Yeah, but as we pivot into this era of mass electrified transport, we're essentially driving these localized power plants managed entirely by software. So we're looking at a diagnostic landscape that is completely invisible and, frankly, deeply unforgiving.
It really is. It forces this, well, a complete paradigm shift in how we define reliability. I mean, the mechanical world allows for graceful degradation, right?
Like a worn part making a noise.
Exactly. A worn bearing is going to whine for months before it actually seizes up. But high-voltage power electronics, they do not afford you that luxury. They operate in a binary state of either perfect operation or catastrophic failure.
And they can transition from one to the other in literally microseconds.
Yeah, exactly.
And what's kind of wild is how thoroughly that complexity is obfuscated from the driver.
Yeah.
You sit in the electric vehicle, you push the power button, the little green ready icon pops up on the dash, and you just put the car in drive.
It feels completely seamless.
It does. But we're looking at a highly technical specification document today, specifically the System HD execution and global safety layer. And we're focusing on two specific diagnostic trouble codes, P0AE1 and P0A2B.
Right. The Precharge Contactor control circuit anomalies.
Yeah, and reading through this, it becomes immediately apparent that the moment between pushing that button and seeing that green light, it's hiding an absolute war zone of thermodynamics and electromagnetism.
It really is. It's a microscopic war orchestrated to protect the vehicle from its own latent energy. I mean, the sheer electrical violence waiting to be unleashed underneath the floorboards the moment you ask an EV to wake up is, well, it's staggering.
Because we're talking about isolating hundreds of volts and hundreds of amps of direct current.
Exactly. And you, as the driver, are placing your trust in these multiple layers of defense hardware, software, statistical process controls that are all operating autonomously before the car even allows itself to move.
Okay, let's unpack this. That is our mission today. We are unpacking the pre-charge sequence. We're going to analyze exactly what happens when this control circuit acts abnormally.
Because when it fails, it is not a small problem.
No, it's a massive problem.
Yeah.
So we're going to dig into the root causes of these failures, the fail-safe architecture, the design and process FMEAs, and of course the brutal validation testing required for mass production.
Torture tests.
It's torture tests, exactly.
Yeah.
But before we dissect those P0AE1 and P0A2B fault codes, we need to map out what this system is desperately trying to prevent in the first place.
Right, the why behind the whole sequence.
Yeah, so when an EV transitions to that ready state, we have a high-voltage battery pack, usually, 400 to 800 volts, ready to deploy. And downstream from that, inside the motor control unit, we have this component called the DC link capacitor, and it's sitting there completely discharged.
And that's the danger zone. Because if you look at the equivalent circuit model of that uncharged DC link capacitor, its initial impedance is essentially zero.
Wait, meaning it acts like a dead short.
Exactly.
Yeah.
It is effectively a short circuit in those first few milliseconds. So if the battery management system, the BMS, were to just blindly actuate the main high-voltage contactors and connect that 800-volt source directly to that uncharged capacitor, the instantaneous voltage differential would be catastrophic.
Like opening the floodgates of a massive dam all at once. The rush of water would just obliterate the riverbanks.
That's a great analogy. The inrush current wouldn't just be high, it would only be limited by the parasitic resistance of the bus bars and the internal resistance of the battery cells. We're talking thousands of amps instantly.
And in the mechanical world, if you introduce that much sudden force to a dormant system, things snap. But in the electrical world, I imagine the points of failure here are the main contactors themselves.
Precisely. Those main contactors are electromechanical relays. So as those metal contacts physically move toward each other to close the circuit, that massive potential difference will actually ionize the air gap between them before they even physically touch.
Oh, wow. So the electricity just jumps the gap.
Yeah, you get a high-energy plasma arc. And that arc vaporizes the metal plating on the contacts. So when they finally do slam together under the force of the solenoid, they're swimming in a pool of molten metal.
Which means they weld themselves shut.
Instantaneously. They micro-weld together, and suddenly you have a high-voltage system that physically cannot be turned off.
Which fundamentally breaks the absolute primary safety requirement, the ASIL-D requirement of being able to isolate the high-voltage bus in an emergency.
Exactly. You never ever want a contactor welded shut. So to prevent this, the engineers introduced the Precharge circuit.
All right, the small bypass valve for our dam.
Yes. Instead of slamming the main contactors closed, the BMS routes the initial current through a parallel bypass circuit. And this circuit contains a precharge resistor and a much smaller precharge relay.
So by forcing the electricity through that resistor, we bottleneck that inrush current. We're artificially limiting the rate of change of the current, letting the capacitor fill up gently.
Right. It allows the DC link capacitor to saturate gradually. And once the voltage across the capacitor reaches parity or, near parity with the battery pack, then the main contactors can safely close.
Because at that point, the voltage difference is practically zero, so there's no arcing.
Exactly. It's called zero voltage switching. Zero differential means zero arcing. And then the precharge relay just opens up, removing the resistor from the active circuit.
It's a really elegant solution, but as the documentation points out, it introduces a massive single point of failure.
It really does.
And that failure is what triggers our main antagonist today, the P0AE1 and P0A2B diagnostics. If this delicate bypass circuit degrades or breaks, the main contactors are totally exposed.
Right, and the system is in critical danger.
So our sources provide this rigorous root cause analysis. It's a four-dimensional breakdown of how this specific circuit can physically and electrically fall apart under pressure.
And the first one is fascinating because it's so counterintuitive. It's the back-EMF assassin.
Yeah, let's start there. Because this failure mode stems from the back electromotive force generated by the precharge relay's control coil.
All right, so to contextualize this, you have to look at the low-voltage control side. The BMS motherboard uses a tiny 12-volt signal to energize a solenoid coil inside that precharge relay.
And that coil creates the magnet that physically pulls the high-voltage contacts closed.
Exactly. Now, energizing the coil is relatively benign. The real threat vector materializes when you turn it off.
Wait, hold on. Turning it off is what causes the massive spike.
Yeah, exactly. It's the whip effect of self-induction. It goes back to Michael Faraday and the laws of electromagnetic induction.
Right, the coil is an inductor.
Yes, and an inductor fundamentally opposes any change in current. So when the BMS cuts that 12-volt supply, the magnetic field that was sustained by that current suddenly loses its energy source, and it rapidly collapses in on itself.
Okay.
And as those magnetic flex lines collapse, they cut across the windings of the coil. This self-induction generates a massive reverse voltage spike that's proportional to the rate of change of the current.
So because the control switch on the motherboard cuts the current in a matter of nanoseconds, the rate of change is astronomical. Even if the coil is small, the resulting voltage spike is just massive.
We're talking kilovolt-level transients. Thousands of volts ringing back down that tiny 12-volt control wire, heading directly into the battery management system motherboard.
So if the low-voltage circuit isn't protected, this kilovolt spike punches right through the silicon.
Exactly. It hits the low-side driver IC, the silicon switch that commanded the circuit in the first place, and it exceeds the dielectric breakdown voltage of the silicon lattice.
It just fries the chip.
Yeah, the gate oxide physically ruptures. It's an electrical overstress event, or EOS. It basically blows a microscopic crater in the chip, permanently shorting it or blowing it open. And suddenly, the BMS entirely loses the hardware capability to actuate the precharge relay.
It's essentially the relay coil lashing back at the motherboard.
Yeah.
That's terrifying. But, okay, that covers the electrical transient failure. The second dimension of failure is purely thermodynamic. Thermal breakdown by abuse.
And the interesting part here is that the abuse isn't coming from a flaw in the system architecture. It's coming from the driver.
Right, because human behavior is the most unpredictable variable in any engineering matrix.
It really is. Think about the primary function of that precharge resistor. It's a sacrificial component. It's designed to absorb kinetic energy and dissipate it as joule heat.
So when you turn the car on, that resistor rapidly spikes in temperature, does its job, and then relies on thermal conduction to just shed that heat before the next drive cycle.
Right, but the thermal mass of a ceramic or wire-wound resistor is finite. It can only hold so much heat. So imagine a driver gets into the car, turns it to ready, immediately turns it off because they forgot their phone, turns it back on, turns it off again to open a door.
They're stacking these thermal impulses on top of each other.
Exactly. They are completely overriding the natural cooling time constant of the hardware. The resistor receives this massive injection of thermal energy, hasn't had time to shed it, and then receives another one.
So the internal temperature just goes off the charts.
Yeah, it quickly exceeds its design parameters, and that's when we start seeing severe thermal expansion mismatches between the resistive wire and the ceramic housing it's built into.
Meaning the wire is expanding from the heat faster than the ceramic shell can stretch to accommodate it.
Right, and that leads to microcracking in the substrate, localized hotspots, and eventually total thermal fatigue. The resistive wire simply oxidizes and snaps.
Wow.
Yeah, the circuit becomes an open loop, it physically breaks, the precharge current drops to zero, and the DC link capacitor remains completely empty.
So the system starves because the bypass lane melted, which leads directly into the third failure mode, physical shorts on the load side.
This one is brutal.
Yeah, this is when the precharge circuit is operating exactly as intended, but it's feeding a catastrophic fault downstream.
Exactly. If the power inverter or the DC link capacitor itself has suffered a failure and shorted to ground, the resistance of the load approaches zero.
So when the precharge relay closes, the current doesn't plateau as the capacitor charges, because it isn't charging.
Right. The current just pours continuously through the short circuit.
But the precharge resistor is only designed for a transient pulse of like 300 milliseconds. Under a hard load side short, it's subjected to continuous high current flow.
And the resistor will eventually fail, but what the documentation highlights here is that the electromechanical relay itself begins to structurally fail under that thermal load.
Wait, really? The relay melts?
It's the metallurgy. The relay contains return springs, usually a beryllium-copper alloy, and they're designed to pull the contacts apart when the power is cut. But if the ambient temperature inside the relay spikes from that continuous overcurrent, those springs reach their thermal annealing temperature.
Oh, meaning the crystal structure of the metal relaxes.
Yeah. The spring loses its tensile strength, it loses its elasticity.
So when the BMS finally realizes there's a fault and cuts the power to the coil, the magnet turns off, but the spring is physically too weak to pull the contacts apart.
Exactly. The relay is mechanically stuck closed. And if the contacts do somehow attempt to open while carrying that massive fault current, you get that secondary failure again. Micro-welding.
The plasma arc.
Yep. Molten metal pools on the contacts, solidifies, and permanently fuses them together.
So we have silicon getting punched through by kilovolt spikes, resistors cracking under stacked thermal loads, and springs annealing until they weld shut. This system sounds incredibly fragile.
It is sensitive, yes.
And the fourth root cause in the document almost sounds boring in comparison, but it's arguably the most insidious because it's purely mechanical degradation over time.
Wear and tear.
Yeah, wire harness wear and tear.
Never underestimate the destructive power of prolonged vehicle vibration. A car chassis is a hostile environment. You have continuous harmonic resonance, thermal cycling, moisture.
So if the low-voltage wire harness connecting the BMS to the relay is routed a little too tight, or if the zip tie fails, that harness just starts chafing against the metal chassis.
Right, the tribological wear over thousands of miles, the insulation slowly rubs away, exposing the bare copper wire.
And if that exposed copper grounds out to the chassis, the control signal never reaches the relay coil. The circuit is dead.
Or the vibration simply work hardens the copper strands until they physically fracture, causing an open circuit. It doesn't have the dramatic plasma arcing of the other failures, but the result is identically fatal. The car won't start.
So what does this all mean? How does the car actually protect you from these physical failures? Because if these four failure modes are known quantities, and this is an ASIL-D safety system, the failsafes can't just be reactive. They have to be incredibly predictive.
They do. To counter these failure modes, the battery management system acts like an ultra-paranoid supercomputer. It relies heavily on a strict physics formula.
Right, the math of survival, the RC time constant.
Exactly. The formula is tau equals R times C. Time constant equals resistance multiplied by capacitance. The architecture doesn't just look to see if current is flowing, it analyzes the exact rate of the voltage climb across that DC link capacitor.
So if the engineering team specifies a 30-ohm resistor and a 1,000 microfarad capacitor, physics dictates an absolute unchangeable curve for exactly how fast that voltage should rise.
Precisely. And the BMS software is programmed to monitor that specific slope. The strict rule is that the capacitor must reach 95% of the total battery voltage within a tiny, heavily guarded temporal window of 200 to 300 milliseconds.
So it's a 300 millisecond race. But wait, why not demand 100%? If we want zero differential across the main contactors to prevent any arcing, Why trigger the main relays at 95%?
That's because of the asymptotic nature of the charging curve. Technically, a capacitor takes an infinite amount of time to reach exactly 100% charge.
Ah, right. It slows down at the end.
Yeah, waiting for it to creep from 95% to 99% yields rapidly diminishing returns, and it introduces unacceptable latency for the driver. You'd push the button and sit there waiting. At 95%, the remaining voltage differential is so low that any minor arcing is well within the wear tolerance of the metal contacts.
Okay, that makes sense. It's a calculated trade-off.
Yep.
But what happens if it loses the race?
Yeah.
If the BMS gives the circuit roughly 300 milliseconds to cross that 95% threshold, and I'm sitting at, say, 50% voltage when the timer expires,
Yeah.
what does it do?
The guillotine protocol. It instantly triggers the P0AE1 or P0A2B diagnostic trouble code and aborts the sequence. The software rigidly commands the pre-charge relay to open. It's a violent, immediate hardware intervention.
Some people might argue that's overly sensitive, right? Like, if you're at 80% at 300 milliseconds, why not just wait another 100 milliseconds? Why execute a hard disconnect?
Because an elongated time constant, a shallow slope, is the primary symptom of a critical fault. It means energy is hemorrhaging somewhere else in the system, like a high-resistance short circuit. Or it means the pre-charge resistor has physically degraded.
So the BMS were to arbitrarily extend the timer, it risks the main contactors eventually closing while a massive load imbalance still exists.
Exactly, which triggers a secondary failure, melting the main contactor shut. So by cutting the pre-charge circuit instantly, the system sacrifices the current drive cycle as an act of self-preservation.
Wow, and once that fault is triggered, the documentation says the global safety layer enforces a permanent lockdown.
It drops into the level 2 safety layer. The system immediately writes a confirmed DTC to the flash memory, the NVRAM of the BMS.
And NVRAM means non-volatile, right? So the diagnostic state survives power cycles. You can't just disconnect the 12-volt battery to do a hard reset and trick the car into starting.
No, you absolutely cannot. It is an anti-tamper mechanism. You are legally and functionally grounding the vehicle. The BMS aggressively locks out the ready state, disables all inverter discharging, and explicitly locks out all charging flows.
So you are stuck.
You are effectively inert until a certified technician physically inspects the hardware and clears that memory with an authorized tool.
It's a harsh penalty, for sure.
Yeah.
But in that ASIL-D context, it's the only mathematically sound decision.
Without a doubt.
Okay, so we know the failures, and we know the software triggers.
Yep.
But let's pivot to the design phase, the design FMEA. How do engineers physically design these parts to survive a severity 8 rating? Let's go back to that kilovolt back-EMF transient we talked about earlier.
The assassin.
Right. How do you silence an electromagnetic whip effect in a confined motherboard layout?
You implement transient voltage suppression, and what's fascinating here is the most elegant solution, the flyback diode.
Hardware armor.
Exactly. A diode, by definition, only allows current to flow in one direction. So during normal operation, the engineers place this diode in parallel across the relay coil, but it is reverse biased relative to the 12-volt supply.
Meaning its cathode faces the positive voltage, so it basically acts as an open circuit. It just sits there doing absolutely nothing while the coil is energized.
Correct. It forces all the current to flow through the coil. However, the moment the low-side driver cuts the power and that magnetic field collapses, the resulting back-EMF voltage spike is generated with an opposite polarity to the original supply voltage.
Ah, so the reverse voltage spike sees the diode, but because the spike's polarity is inverted, the diode is suddenly forward biased. It becomes the path of least resistance.
Yes. The spike hits the diode and loops immediately back into the coil itself. That massive transient energy never travels down the wire to the sensitive silicon chips. It just circulates harmlessly within that local coil diode loop until it dissipates as minor heat.
It's a brilliant utilization of physics to just neuter a high-voltage thread. But the spec sheet notes that even with that diode, the silicon switches themselves, those low-side drivers, are no longer just dumb transistors.
No. DFMEA mandates the use of highly integrated automotive-grade smart chips. A standard MOSFET will just blindly flow current until it destroys itself.
Right.
But these smart ICs contain integrated logic gates monitoring their own internal states. They have built-in self-diagnosis for overcurrent, overheat, short circuits.
So if the chip detects a short to ground, or if it gets too hot, it just autonomously severs the connection itself.
Exactly, and it does it faster than the main microprocessor can even query it.
That handles the electrical transients perfectly.
Yeah.
But I want to talk about how the software addresses the human abuse factor, that stacked thermal loading from rapid key cycling we mentioned.
The abuse testing, right?
Yeah, you can't fit a refrigerator-sized heatsink onto that tiny pre-charge resistor. So how does the software govern the thermodynamics of a physical component?
By running a continuous dynamic thermal estimation model in the background. It's universally known as the I-squared-TED algorithm. And this isn't just a simple lookup table. It is mathematically integrating the square of the current over time to calculate the exact joule heating taking place inside the resistor element in real time.
It sounds exactly like a video game stamina bar.
Yeah.
Like if you deplete the stamina, you have to wait to recharge.
That is a perfect analogy. The BMS calculates a virtual thermal mass. It knows the specific heat capacity of the resistor and the ambient cooling rate, and it enforces a strict retry counter.
So if a driver attempts to start the car, the software checks that I-squared-T stamina bar.
Exactly. If the virtual temperature is safe, it allows the sequence and adds that new heat impulse to the thermal model.
But if the driver cycles the ignition, say 3 times in 60 seconds, that virtual temperature spikes closer and closer to the material's melting point.
And on the fourth attempt, the algorithm looks at the projected temperature curve, sees that another cycle will exceed the structural limits of the ceramic substrate, and decisively intervenes.
It just ignores the driver.
It completely locks you out. It locks the pre-charge relay out until the mathematical model calculates that enough time has passed for the resistor to cool down naturally.
It is pure preventative logic, shielding the hardware from the driver, which is incredibly robust in theory. But theory often falls apart on the factory floor, right?
Oh, absolutely.
We can design the perfect software model and the perfect flyback diode, but if the component is soldered poorly, the system fails. So let's look at the process FMEA, how factories control the manufacturing variables to actually achieve zero defects.
The 5M1E variables: man, machine, material, method, measurement, environment.
Right. The transition from CAD drawing to physical assembly line introduces microscopic vulnerabilities.
Let's look at that flyback diode again. Its entire protective function depends on being installed with the correct polarity. If a pick-and-place machine puts it on backward, it isn't a protective valve anymore. It's a dead short straight to ground the moment you turn the system on.
And at mass production scales, thousands of boards a day, you obviously can't rely on a human quality control inspector looking through a magnifying glass.
No, you rely on relentless microscopic quality control. The orientation and solder volume of that diode are designated as key control characteristics.
KCCs.
Right. To guarantee zero defects, the line utilizes 100% 3D automated optical inspection, or AOI, combined with 3D solder paste inspection, SPI.
Explain the mechanism behind that 3D SPI for me. How is it measuring the volume, not just the flat area, at a micrometer scale?
It uses phase shift profilometry. The machine projects a structured pattern of light, usually shifting more fringes onto the bare circuit board right after the solder paste is applied.
Okay, before the components are even placed.
Exactly. High-speed cameras capture how those fringe patterns distort as they drape over the microscopic mounds of gray solder paste. By calculating the phase shift of the light, the software reconstructs a highly precise, three-dimensional topographic map of every single solder pad on the board.
Oh, wow. So it's calculating the exact cubic volume of the paste to make sure it's perfect. Because what? Too little means the diode shakes off from vibration, and too much means it might short circuit to an adjacent path.
Exactly. But that optical inspection on the motherboard is only half the battle. The PFMEA highlights another critical manufacturing process that's just fraught with physical peril: the application of the thermal interface material, or TIM.
Ah, the bubble battle. Applying this thermal paste sounds exactly like putting a screen protector on your phone. Like if you get an air bubble under your screen protector, it's just annoying. But here, an air bubble is deadly.
Yes, a bubble here will destroy the component.
Yeah.
The resistor generates a massive amount of concentrated heat, and it relies on physical contact with a cooling plate to survive.
But metal and ceramic surfaces are microscopically bumpy, right? They don't mate perfectly.
Right, so you inject thermal paste to fill those microscopic voids. And the primary function of the TIM is to displace air. From a thermodynamic perspective, stagnant air is a superb insulator. It's terrible at conducting heat.
So if the automated nozzle traps a macroscopic air bubble between the resistor and the cooling plate.
That localized area loses its thermal dissipation path entirely.
Wow. So while 90% of the resistor is shedding heat safely, the 10% sitting directly over that trapped air bubble just bakes.
You get severe localized heat soaking. And the I-squared-T software model assumes uniform cooling, so the computer has no idea this hotspot even exists till the thermal gradient physically fractures the ceramic.
So how do you inspect for a void hidden completely underneath the solid component. You can't use a normal optical camera for that.
You use automated active thermography. The inspection station pulses a brief, highly calibrated current through the pre-charge resistor to generate a controlled thermal wave. And an infrared thermal imaging camera continuously monitors the surface temperature.
Okay, so in areas where the paste is perfectly applied, the heat rapidly conducts away into the cold plate, so it shows up as dark and cool on the IR camera.
Exactly. But over an air bubble, the thermal energy reflects back to the surface.
Because it has nowhere else to go.
Precisely. The surface temperature directly above the void spikes, and it glows brightly on the infrared sensor. If the automated vision system sees that the aggregate area of those bubbles exceeds 10% of the total surface, the assembly is flagged and immediately scrapped.
It's a remarkable fusion of electrical stimulation and thermodynamic imaging. And this leads directly to the end-of-line testing, the EOL. The battery pack is fully assembled. Before it leaves the facility, it has to pass a 100% pre-charge slope scan.
Right. They connect the high-voltage terminals to a massive load simulator and command a pre-charge sequence. The EOL tester acts as a high-resolution oscilloscope, plotting the real-time voltage curve as the internal circuit charges.
So it's looking for any slight deviations in that tau equals R times C slope. If a supplier provided a batch of resistors that are technically within spec, but leaning heavily toward the upper limit, the tester will see the voltage climb just a fraction of a millisecond too slowly.
Exactly. It catches stacked tolerances before they become real-world failures. If the curve fails to perfectly match the theoretical master design trace, the pack is quarantined.
It's the ultimate safeguard. So we have the design locked in and the manufacturing process heavily scrutinized. But none of this matters until the system survives the design verification plan and report the DVP&R phase.
Here's where it gets really interesting.
This is the torture testing. This is where engineers mathematically and physically attempt to destroy their own creations to validate the safety margins before mass production. Let's look at the 4 torture tests outlined in the sources.
It's an exercise in worst-case scenario validation. Torture Test 1 targets the integrity of the I2T thermal software model. They place a completed battery pack inside a heat chamber set to a blistering 50 degrees Celsius.
Basically, heat-soaking the entire system to simulate a vehicle parked on black asphalt in the middle of a desert summer. The cooling capacity is already severely compromised.
Exactly. Once the system achieves thermal equilibrium at 50 degrees, they use a simulator to violently cycle the ignition. Key on, key off, key on, key off, executing the pre-charge sequence as rapidly as the hardware allows.
Force-feeding thermal transients into the resistor. What are the passing criteria here?
It's twofold. First, they have lab-grade thermocouples physically glued to the resistor. The actual physical temperature data is continuously compared against the virtual temperature calculated by the software inside the BMS.
And the standard is that the software's estimation must be within plus or minus 10% of reality across the entire thermal curve, right?
Right. The math has to perfectly mirror the physics. If the algorithm hallucinates a lower temperature than reality, the system burns. Second, on the 4th consecutive pre-charge attempt within a 1-minute window, the software must unconditionally lock the relay.
It has to prove it can autonomously deny a start request.
Yes. And then they leave the system in that 50-degree oven to observe the cooldown. The software must correctly calculate the degraded thermal convection rate and only safely unlock once it actually cools.
Unbelievable. That brings us to torture test 2, the 10,000 cycle whip. This is verifying the flyback diode against that back-EMF spike.
The methodology here is brutal repetition. They open and close the relay over 10,000 times while monitoring the 12-volt control line with a high-speed oscilloscope sampling at greater than 1 gigasample per second.
Let's pause on that. Why do you need to take 1 billion voltage readings every single second to monitor a 12-volt switch?
Because of the extreme velocity of inductive transients. When that magnetic field collapses, the voltage doesn't ramp up linearly. It spikes almost instantaneously. The peak of that kilovolt transient might only last for a few nanoseconds.
So if you use a standard diagnostic oscilloscope that only samples at like 100 megasamples per second, the time between readings is too vast.
Exactly. The voltage could spike to 2,000 volts and collapse back down entirely between 2 data points. You would literally miss the lightning bolt because your shutter speed was too slow.
By using a 1 gigasample per second rate, they guarantee they captured the absolute peak amplitude of every single back-EMF event across all 10,000 cycles. And the flyback diode must trap those spikes flawlessly every single time with zero physical damage.
If the oscilloscope captures even a single microsecond where the voltage exceeds the chip's limits, the test is an instant failure. 10,000 cycles of perfection.
Which leads into torture test 3, the bubble test. This is fascinating because it's the only test where the engineers intentionally sabotage their own hardware.
It's the ultimate validation of the factory controls. They deliberately build compromised battery packs. Group A is perfect, less than 10% bubbles. Group B is intentionally manufactured with 15% bubbles. Group C is severely sabotaged with 30% or more bubbles.
They're building localized hotspots directly into the hardware, and then they pump massive power through them at 50 degrees Celsius. What's the result?
Group A must stay below 120 degrees Celsius, but the real test is that groups B and C must be successfully caught by the factory's end-of-line cameras, maintaining a process capability index, a CPK of greater than or equal to 1.67.
Let's unpack that metric. In statistical process control, what does a CPK of 1.67 actually signify?
It pushes us into the realm of Six Sigma quality. It guarantees that the infrared camera system is so finely calibrated that the statistical probability of a sabotaged battery slipping past the inspection station is less than 1 in a million.
It proves the factory floor is as mathematically robust as the software.
Which brings us to the final hurdle, torture test 4, the final checksum.
Right, the final lock on the gate. Yeah, after surviving the heat chambers, the billion sample per second monitoring, and the Six Sigma validation, the system implements a cryptographic lock.
So that end-of-line dynamic pre-charge scan we talked about, the DVP&R mandates that the physical slope measured by the test rig must align within a razor-thin plus or minus 5% tolerance of the master design curve.
And in an environment managing hundreds of amps, a 5% margin of error leaves absolutely zero room for compromised parts.
If it passes, the system generates a cyclic redundancy CRC32 checksum based specifically on the physical parameters validated during that test. It writes that foolproof digital signature directly into the non-volatile memory of the BMS. No checksum, no leaving the factory.
It's a digital wax seal, cryptographically binding the physical hardware's verified performance to the software's boot logic. The sheer depth of the paranoia is just staggering.
It really is.
Let's pull back and look at the macro picture here. We started this deep dive exploring the P0AE1 and P0A2B diagnostic codes. But what those codes represent is the tip of an immense engineering spear. When you sit in the driver's seat and ask the vehicle to wake up, you are initiating a 300 millisecond sequence where this entire architecture engages. A smart IC checks its internal temperature. A coil creates a magnetic field. A precharge resistor absorbs a massive surge of energy, while an I2T algorithm maps its thermodynamic state.
And the RC circuit dynamically models a voltage slope demanding 95% equalization in a fraction of a second to prevent plasma oozing.
Right, and when it finishes, a reverse bias diode catches a kilovolt electromagnetic transient before it can crater the motherboard. All of this, bound together by Six Sigma manufacturing tolerances and cryptographic checksums in less than 300 milliseconds, just so you can safely turn on your car.
It fundamentally challenges our perception of the consumer interface, That seamless green, ready light on the dashboard is an illusion of simplicity deliberately crafted by engineers. Every time you turn a key or push a start button, you are initiating a highly volatile sequence of electrical forces that naturally want to destroy the machinery housing them. We are safely navigating this power solely because of the relentless, microscopic paranoia baked into the functional safety architecture.
It forces you to look at every electronic device, every vehicle, every piece of heavy machinery with profound new respect. I mean, if this staggering level of material science, mathematical modeling, and brutal physical torture testing goes into securing just the first 300 milliseconds of an EV's operation, what does that say about the immense unseen layers of engineering keeping the rest of our modern technological world from tearing itself apart?
Something to think about the next time you press a power button.
Absolutely. Thank you for joining us on this deep dive into the invisible armor of high-voltage execution. Until next time, look a little closer at the machines you trust.